Hi everyone, I'm Reza and this is session 4 from the video tutorials of PRISMS-Plasticity. In the last session, we went over the input files of the PRISMS-Plasticity typical simulation. In this session, we will actually simulate one sample and we'll post-process the results so you can get familiar with the type of output you can get out of PRISMS-Plasticity simulation. I assume you compiled deal2 on PRISMS-Plasticity using the previous video and you git clone plasticity folder from the PRISMS-Plasticity GitHub. We are in the plasticity folder right now. This has been compiled before, so we want to go to the applications folder, crystal plasticity. So these are the applications we have in this folder for different crystal structures. So let's start with the simplest one, Fcc Compression. This folder was the one that we went over in the last session. Today we actually want to simulate this sample. So let's take a look at the main parameters input files. So vim prm.prm. So this is the input file. We went over it last video. So the size of the sample is 1 in all 3 directions. For the discretization, we have subdivisions in x, y, and z equal to 1 and set refine factor equal to 3. This will end up with 8 by 8 by 8 FE mesh. The macro structure that we are trying to model is 32 by 32 by 32. So when you are modeling a 32 by 32 by 32 macro structure by 8 by 8 by 8, you over coarsen the sample. But here we don't want to worry about the accuracy of the simulation. For this step, we just want to see what type of results we will get out of this simulation. So we leave this as it is. For now, we don't want to have any output visualization printed out. So we just want the stress strain output and post-process that in the first step, and the total time is 5. The time increment is 5 10 to power minus 3. So let's open the boundary condition input file. So you can see that the first phase is constraints in all 3 directions. In x direction, on the other phase, you will compress the sample. So as I showed you in the last video, this will mimic a boundary condition of uniaxial loading. So in this simulation, considering the size of sample, which is unit, we are applying minus 5% compression. Before we move further, maybe we cannot get this sample done in a timely manner. So we will coarsen the mesh one step further. So let's coarsen the mesh to 4 by 4 by 4 by set the refine factor equal to 2 and save this. And then let's make the compression instead of minus 5% minus 1%, and then use 4 processors to run the sample. So to do the simulation, the command is mpi run -n. 4 is the number of processors, the address of the main executive, and name of the parameters input file. After 1000 increments, the simulation is over. So you can actually see the total required time to do the simulation and the required time for different parts of assembly, mesh and initialization, solve, and post-processing. So let's see what's changed in the folder. So you can see that there is a new folder created with the name of results. So if you go to the results, you'll see there is only one file in it. The reason that we have only one basic file is we turned off the post-processing file generation in the input file. So first step is to just fully discover what are the components of stress strain.txt. So to see that, let's vim stress strain.txt. So this file include the macro responses of the sample, including stress strain, and in the case of having twinning, you will have twin volume fraction and twin made, and the total sleep you have in the sample. But the better way of post-processing this output is to open that in the Excel file. So when you open the stress strain.txt file in the Excel, you will see this box. So you will just choose delimited and then click on the finish button. So this is how it will look like in the Excel file. The first 6 components are the components of the green strain tensor, and the next 6 are the Cauchy stress tensor. So let's plot the absolute value of strain along the x-axis versus the absolute value of the stress along x-axis. So basically this is the axis we're applying the compression, but just for the sake of representation I just use the the absolute value. You can see that both strain and stress along x-axis are negative, and the strain increment is -1 10 to the power -5. So let's plot strain versus stress. So to do that, scatter. So this is the stress strain curve for your sample. You should be careful. Typically, strains which are reported are either engineering strain or true strain, but the values we have here are green strain. So to generate the engineering strain in the case of uniaxial load, we know that we are applying the increment strain of 1 times 10 to the power -5. So we put that value here and then add that for each increment all the way to the last increment. But you should be careful. The stress reported here is actually true stress. It's not engineering stress. In the next step, you want to calculate the true strain. To calculate the true strain, the sign of the strain is important. So first, we need to have the engineering strain with the correct sign. Since the sample is subjected to compression, the correct sign for normal strain along x-axis will be negative. So we add a column here. We basically want to have the engineering strain with the correct sign, which in this case it's negative, and we apply this to all increments. Now, in order to get the absolute value of true strain, absolute ln 1 plus the engineering strain with the correct sign, and that's it. We apply this to all increments and we have true strain, the absolute value of true strain. This is the absolute value of true stress. We had it before. It's basically the normal true stress, which is normal Cauchy stress along x-axis. So we can simply plot the absolute value of true strain versus the absolute value of true stress using insert scatter, and that's it. This is an average behavior of the whole sample, so it can be very helpful for calibration or just to simply check the simulation. One important thing is you can go to the last increment. Here actually you can compare different strain definition. So this is the absolute value of true strain, this is the absolute value of engineering strain, and this is the absolute value of green strain tensor, the normal component along x-axis. See, the difference is very small, but if you go to the larger strains, this difference will become very important. So what other type of output we can get out of PRISMS-Plasticity simulation? Let's increase the number of elements to have a more realistic simulation. So let's open the PRM file and increase the number of elements to 32 by 32 by 32 by increasing the refine factor to 5. Actually, 32 by 32 by 32 will match the voxelized macrostructure you have. So each macrostructure voxel will be modeled using a single element. Also, we want to this time actually generate an output besides the stress strain.txt. So we put set right output to true, and let's put a skip output steps equal to 5. So it means each 5 increments it will output these fields for you: equivalent strain, equivalent stress, grain ID, and twin fraction. So let's go back. We increase the number of FE mesh to 32 by 32 by 32. So compared to the previous simulation, this simulation will be slower. Here we'll just kill the simulation after 10 or 5 increments depending on the speed. Just show you the typical post-processing results. So let's say MPI run. We're using 8 processors, main, PRM. So you can see there are some lines before the increments are starting. Twinning is not enabled because we didn't enable twinning in the parameters input file. Then it reads the voxel data file grain ID here, reading the orientations, generating the problem mesh, and we're using 8 processors, and the number of elements are slightly more than 32,000, and the number of degrees of freedom, and reading boundary conditions, and then the main simulation will start. So you can see that the simulation is way slower than the previous simulation, which has 4x4x4 FE discretization. So we will kill the simulation after the first set of post-processing files are out. You can see that here in the increment increments, we don't have that output written to, but here as the 5th increment, be careful, start with number 0. At 5th increment, we are having them outputted. So we kill the simulation. Let's go back to the results folder. Now you can see that in addition to stress-strain.txt, there are 2 other types of files: project fields and solution. Solution will have the deformation information in X, Y, and Z direction, while project fields, it includes the stress and strain information along twinning or any other additional output variables you define. But also you can see that because we are using 8 processors, in addition to the main file which has the extension of PVTU, there are 8 more files with the numbers at the end, which is starting from 0 to number 7. So these are separate output files written by different processors. We used 8 processors, so the numbers are from 0 to 7. This is actually how we parallelize the output procedure, which could be a bottleneck if you don't do that in a very big simulations. So 2 files that we are dealing with right now will be project field PVTU and solution PVTU. And this number is the number of increments that you've actually written out. To process these files, we can use ParaView. So in the next step, we open 2 files of project fields PVTU and solution PVTU in the ParaView to show you what you can do using those files. So after you open the file project fields PVTU, you'll get something like this. So let's see the macro structure first. So we change the solid color to mesh grain ID. So this actually shows you the macro structure you inserted into the sample. Why? Because you're using the 32 by 32 by 32 voxelized mesh, so you can exactly mimic the input macro structure using the 32 by 32 by 32 finite element mesh. And if you add surface with edges, you can see that the finite element discretization on top of it. In the next step, you can visualize the equivalent strain and equivalent stress in the sample. So you can do all the post-processing features you want using the ParaView, but another file that you want to open is the solution PVTU. So let's open the solution PVTU. So if you open the solution PVTU, you will get something like this. Again, you can use the mesh grain ID to get a macro structure. So it's basically similar to what we've just done. But if you want, now you can get actually the U along X, along Y, and along Z direction. So you can get a deformation map actually in the macro structure. So here we were applying the load along X axis. So let's plot the UX. So you can see here is the negative displacement you applied on the left side all the way to 0, which is the constrained edge. So what you can actually do is you can use the feature of ParaView to show you the deformed body. So for that, you can use the filter wrap by vector and apply it. And then you can use the scale factor. So you can increase the scale factor to see more and more. So I think 1000 will be enough. So you can see that here you can actually see the deformed body compared to the initial body. This is really good for the initial visualization, but what if you want to actually process these data or process other data like the stress or strain at each integration point throughout the body? Then we need to go to the next level of outputs, quadrature outputs. So what if you want to have the stress or strain or any other variables for each quadrature point? Then we need to modify the parameter input file and add 2 lines to it. So let's go back to the command line and let's go back to the Fcc Compression folder. Now we open prm.prm. So you need to add 2 lines to the input file. So the first line is set right quadrature output true, and the next line is set skip quadrature output steps. So here basically you define number of quadrature output steps to skip. So we put it here 5, similar to the other type of outputs we just processed, and close the parameter input file, and then npm run n8 main simulate the sample again. So this time, after 5 increments, when we kill the simulation, we'll get another new file. We'll see that. We killed the simulation after the 5th increment. Now you can see that in addition to projecting post-processing fields, you will have a new line, writing quadrature data to file. So if you go to the results, you'll see a new file, quadrature output 4.csv. So this number 4 is the increment number this quadrature output belongs to. So let's open this using Microsoft Excel and see what does this file include. So this file includes the information for each quadrature point. So each row includes the information for one quadrature point. So if you go all the way down, you will see that you have 262,144 quadrature points. You can calculate that actually. You have 32 by 32 by 32 elements, and each element has 8 quadrature points, so you will get the same number of quadrature points. But what are the informations we include here? What I typically do here is I add here and write one by one what does each of these columns mean. So the first one is grain ID for that integration point. The next one is what is the phase if you have multi-phase, otherwise it will be 1 for all the integration point. Be careful, if you're using advanced twin model, this column will be deleted. So the next column will be the determinant of the Jacobian for that integration point. The next column defines if the quadrature point is twinned or not. So it will be either 1 or 0. So it's twin. The next one gives you the x, y, and z of the quadrature point. So x, y, and z. The next 3 columns are the updated Rodriguez vector for each integration point. So row 1, row 2, row 3. These 3 columns are very important because if you want to plot updated pole figures, you should actually use these 3 columns, and we will go over that later. The next 9 columns are the components of the elastic deformation gradient. So FE11 all the way to FE12, FE13, FE21, FE23, FE31, FE32. The next 9 columns are the plastic deformation gradient tensor, the 9 components. So you can just copy this and paste as FP. This should be actually FE22, and this will be FP22, FP33, FP12, FP13, FP21, FP23, FP31, FP32. So after that, you'll have 9 Cauchy stress tensor components, which you would actually need 6 of them because it's symmetric, but we'll have them. So let me adjust the width of these columns. So this will be T11, so the same, T22, T33, T12, T13, T21, T23, T31, T33. So after that, depending on if you're using the advanced rate dependent model or not, you may have some extra columns. But since we don't use the rate dependent advanced model, we just will have the next column as sleep fraction. The next columns are sleep fractions for each sleep system. Typically in FCC, BCC, HCP, you will have 12, 18, 24 sleep systems. So you may need 24 of these columns. But if you're using advanced twin model, each quadrature point can have many twin children, which each of those can have 12, 18, or 24 sleep systems. That's the reason we predict maximum you will have 84 sleep systems. So if you go all the way to the next 84 columns, they're all sleep fraction. In our simulation, we have FCC sample with 12 sleep systems. So we just care about the next 12 columns, and we should delete all the way to the 84 because we don't need them. So we will have sleep 1, sleep 2, all the way to sleep 84, and then delete the columns after 12. So the next 6 columns we designed are for twin fraction system. So it reports the twin fraction you have for each integration point. So these are twin fraction 1 to 6. If you are using advanced twin model, you will have way more number of columns for twin output fraction. So the next question is, how can we actually see what are each these columns are? Or if we want to add another variable to these columns, what should we do? So to modify or view these columns, we should open the PRISMS-Plasticity GitHub files. So we open a Google and then type PRISMS-Plasticity GitHub, then open this. Now we can open the folder source and then material models and then crystal plasticity and open the file update after increment.cc. So update after increment includes many of the functions that we have after each increment is converged and you want to do any post calculation. So if you go all the way down to the line 220, this is the part that you actually will print out the required quadrature points information. So for example, you can see that the first information is cell orientation map, which is the grain ID. The next one is phase. The next one is the Jacobian for each quadrature point. The next one is if it's twinned or not. The next 3 are the x, y, and z of the quadrature point. The next 3 are the root nu, which are the updated Rodriguez vector for each quadrature point. The next 9 are elastic deformation gradient and then plastic deformation gradient and Cauchy stress tensor. If you have advanced rate dependent model, you will have extra variables, which are advanced parameters. You don't need to worry about them now. And after that, you will have sleep fraction converged, which are the sleep fraction you have for each quadrature point until all the way down to 84, start from 0. And then you will have twin fraction converged. And if you have advanced twin model, you will have 24 more. But be careful. There is an important part of this, which if you are using user material model, it means that you define your own constitutive model. You might define some state variable for your simulation. Then if it's the case, we also add those, like 51 of those here, to track the state variable for each quadrature point. And that's it. So this was brief overview of 3 types of output you will have in the simulation using PRISMS-Plasticity. In the next session, the pole figures of the simulated sample will be plotted as an important result of CPFE simulation. Thanks for watching this video.